Okay. Excuse me. Hello, everyone. Happy Friday. It's been a long, busy week for me. I hope you all had a good week. I'm here with my good buddy, Franklin. And this week, we are going to be talking about one of the more dreaded topics that we cover in this course. We're going to be talking about recursion, or as my buddy Franklin might call it, recursion. Haha, no, that was terrible. Alright, I've already created the repository for this studio, and so what I'm going to do is go through and complete the studio from start to finish and review the recursive concepts, the important ones, because they're all going to show up on the homework assignment. But I'm also going to spend a significant amount of time going over the homework assignment, giving you some tips on each and every part of it, and especially that last part, max path length. So if you are watching this video and working on assignment 6, you may want to, take a look at the end of this video for some tips on those specific problems, if that's what you came here for. I'm going to go ahead and get started on this studio, though, and we want you to do these methods in a couple of different ways. So you can see that for all of these methods, we ask you to do it twice. Oh my goodness, excuse me, that was my lunch. All right, that was disgusting, I apologize. So we are going to take a look at these iterative methods first. So for example, geometric sum, I can see that we create a sum variable, we iterate through, and we then compute the next term as follows, right? Until we finally return our sum. This is actually an example of the accumulator pattern. We've seen this pattern before. Likely we'll see it again. Anytime I'm computing a sum or a running total of sorts, the accumulator pattern is a good choice. So this is how we would do it iteratively, and I feel like at this point most people can look at this and dissect it pretty simply. But we're now asking you to do the exact same thing recursively. And to understand, why we are making this comparison between the loops and recursion, keep in mind that they're both used to do the same thing, which is repetition. So just like this loop is used to perform something multiple numbers of times, we also use recursion for that same purpose. The main difference is that instead of using a loop to accomplish this, we are using the method. So we're using the method calls to accomplish the repetition instead. By essentially telling the method whether it should continue, i.e. make a recursive call, or whether it should stop when we have hit the base case. So one thing that I think is important to notice is, as you go through, is that you can see all the pieces that we see here with this iterative solution show up in the recursive solution. We think about the base case, for example, which is where I typically like to start with a recursive method, is the base case. So when do we quit here? If I take a look at this iterative method, you can see that I've got a couple of options. So I can stop, I actually start at 1, right? And then I stop at n, by the way that this loop is written. So those are my two options, I think, as in terms of my base case. That makes sense to me, right? So if I try to think of it in terms of n, that would mean that I try to mimic the loop as closely as possible, starting at 1, counting my way upwards towards n, right? Summing the terms up along the way, as opposed to starting at n and working my way down towards 1. The reason why we typically prefer our base case to be these smaller values, like I'm about to select 1 as my base case here, as opposed to using n as my base case, is because for these small, simple values, I typically know what the answer is. So the geometric sum for 1 is known, or if it's not directly known, it's very easy to compute. It's just going to be, right, 0.5 to the 1 power, or 1/2. So I can use that known value as my base case. The base case is often going to be some known value that we can just code into our if statement. So if n is equal to 1, we know what our answer is. We're going to return 0.5. Otherwise, we now have to perform some sort of repetition. So the loop does that by incrementing the power every time we go through the loop by adding 1 to the power. Since we're starting at n and working towards our known base case, right, that tells us that we maybe have to work a little bit backwards here. So we have to work by decreasing the power every time. And since this is the repetition, since the power is essentially based on our input parameter here, n, right, that sort of starts to give us the feel for what our recursive call is going to look like. Somewhere in here, I expect to see something that looks like geometric sum of n minus 1. So if you tell me to compute the geometric sum of 3, I'll take a look and say, no, that's first I need the geometric sum of 2. Then I hit the geometric sum of 1. There's my base case. All right, now I can figure out what the answer is. But I'm not doing any addition here yet, right? There's no addition happening yet at this particular moment. And so consider what this formula actually looks like. We're going to do 1 over 2 to the 1, 1 over 2 to the 2, 1 over 2 to the 3, etc., etc., etc. So every time we go through an iteration in this loop, for the iterative version, every time we go through this iteration, through this loop, we're computing one more of those terms and adding it to our sum. So let's try to mimic that process. I'm going to compute the term for whatever this value of n is, right? So I'll say math.pow of 2 to the n, or actually it was written as 0.5 to the n, I believe, right? And then I can add that to the geometric sum of n minus 1. Or another way of thinking about this is, what are we upset about here? Let's take a look. The left-hand side of assignment must be a variable. Sure, we can store this in a variable if we would like to. Or we could also just return it. I think that's also an acceptable option. This is no longer necessary. Right, so another way of stating what this line of code does, if we go back and take a look at the formula here, we can see that this shows us the first four terms of the geometric sum that are computed. So in order to compute the fourth geometric sum, where n is equal to 4, right? I first need to compute the geometric sum of n is equal to 3, and then I add one more term onto it. In order to compute the geometric sum for the first 3 terms, I first need to compute the geometric sum for the first 2 terms, and then I'll add the third term onto it. And that is in effect what our code is mimicking. We have defined geometric sum in terms of itself. To compute the geometric sum of n, I first compute the geometric sum of n minus 1, and then I add this other term onto it, right? Since n minus 1 is gravitating closer, we know that n is going to be positive, so n minus 1 is going to gravitate closer and closer to our base case. That should guarantee that we'll eventually hit our base case and stop the recursive calls from happening. But we've provided you with some tests, so let's go ahead and try it and see how it goes. I'm sure I messed something up. So for 0, it doesn't work, right? All right. Let's add another case for 0. Actually, I suppose I could just do this for 0, right? If I could just plug in what the value for 0 should be, which is, what should the value for, oh, it should be 0. Let's see if that does it. There we go. Just tweaked my base case a little bit. I didn't stop early enough for the tests, or I stopped too soon, rather, for the tests. I actually want to step through this one more time, though, and show you how this works for a particular execution. I don't know that I'll have time to step through each and every one of these recursive functions with the debugger, but I do want to show you how to use the debugger with these recursive methods. A, because I think it gives you a clear idea of how these recursive methods work, and B, because I want you to understand how to do this with your own work as you're working on the homework assignment this week. So you'll notice that what I have done here is I've set a breakpoint on the line with the recursive call. And actually, I'm going to tweak this a little bit. I'm going to just modify this a little bit to insert this as a variable. The reason being that once I run the debugger, I'll be able to inspect the value of this variable, which is going to be useful to us as we examine the execution of this code. Oops, missing a semicolon out here. Okay. And so what I'm going to do next, instead of running through the tests, I want to have a little bit more control over it than that. So I'm going to go ahead and come down here and put in a main method. We've sort of gravitated away from main methods for a moment in, in exchange for these unit tests, but main methods still exist and we can still use them. Main methods are the entry point to a program. So if you want to, make a little bit of code to write a little bit a test for yourself, like I'm about to do, you certainly can. So I'm going to go ahead and put in a call to geometric sum down here. We'll do 4. We'll do the 4 example like I was talking about. Okay. I will now go ahead and start up this file in the debugger, recursive methods, since that's the file that I wrote my main method in. And let's see what happens. So notice I plugged in the value of 4. So when the debugger starts up, all right, because actually I'm going to start that over one more time. You'll notice I put my breakpoint on line 20, or I put it actually on this line, and then I wrote more code, but I didn't move my breakpoint. I actually want to move it up to line 19. So I'm going to stop this execution and start it over again with the breakpoint on this line now. All right, so here we are. This is our first trip through the geometric sum method. The value that's been plugged in for n is 4, which you can see over here in the variables window. And so it's going to go off and it's going to try to execute this line of code. We can go ahead and compute this term here. That's not a problem to compute this value. But in order to do this, we actually have to go off and execute this method again with a new value for n using n minus 1. In order to see that execution in the debugger, we have to do something a little bit different. So up here in the top left corner, we're used to using the step over button to move on to the next line of code. There's another way that we can perform a step called step into. And we use this step button when we wish to step into a method call, when we wish to go into the method call and see how that method is going to work. So as you go through your code in the debugger, you should be thinking, do I need to know how this method works? Do I need to step into that method and see what it looks like? If the answer is no, then you should use the step over to move over that line and examine the next one. If you would like to move into that method and examine how that method works, then you can use step into, which I'm about to do. And so here we can see a couple of things happened. My value for n is now 3. It's now 3. And over here on the left, this is what's called the stack trace. So you can see that the first method call to geometric sum is still here. In fact, you can even click on this and the value for n will change back to 4 and show you that this method is still on line 19, just where we left it, waiting on the next method call to geometric sum, the recursive call, to finish doing whatever it needs to do. So this is where we are at right now, line 16. So there's no methods on this line. I'm gonna click step over, and actually I don't really care about anything that happens until I get to this line, the recursive line again. I haven't hit my base case yet. N is equal to 3. So here's the recursive call again. I want to step into that. So I'm going to hit step into. I now see n has gone down to 2. I now have a third version of this, but the other ones are still there, right? There's the one for n is equal to 3. Here's the one for n is equal to 4, still sitting there and waiting for all of us. Now to finish up, we're going to do this one more time. Step over. Here's another recursive call. All right. I now see 4 methods on my stack, with the main method all the way down here at the bottom, by the way, which will always be the case since the main method is the entry point into the program. I would always expect to see the main method on the bottom here. I finally hit the case, however, where n is equal to 1. So here we can see, all right. Oh, wait, actually, I'm not in my base case yet. My base case is n is equal to 0. So let's move one more time. 5 method calls. All right, n is equal to 0. That's our base case. So this time, no more recursive calls. I hit the return statement. 0 is the answer. The geometric sum of 0 is 0. So the next time that I hit step, where am I going to go? This method is over. So you'll notice that the method call stack shrank by 1. I am now back in the version of the method that exists where n is equal to 1. But I now have my answer. You can see it's telling me that the previous version returned 0. So 0 is my answer here, plus whatever this value expects to be. And now I can see that that sum gets computed as 0.5, which is my return value. Okay. Here I am now in the version of this method where n is equal to 2 with my return value of 0.5 computed from the previous recursive call. I'll now compute the next term, add it on. That gives me 0.75. I'll return that value. I'm going to keep repeating this process, working my way back up the method call stack until I finally return back to my original method call where n is equal to 4. This is the one that kicked off the whole recursive process. You could see our repetitions there, right? You could see the repetitions. We drilled all the way down to our base case, and then the work actually happened on the way back up. That was kind of interesting to see, right? We actually did all the computation on the way back up. But that's how all recursive calls are going to behave. I'm going to keep calling the recursive method, keep calling it, keep calling it, keep calling it until I hit that base case. And then I have to work my way all the way back up. Whether I need to compute something on the way back up or not, it doesn't matter. My recursive calls are still going to follow that process of returning and moving their way back up the method call stack until we get to the original recursive call, which is what we've done here. We can finally return our final answer. So this is our final computed sum, 0.9375, which I'm going to assume is correct because computers are good at computing. And that is a good way to use the debugger with your recursive programs. I hope illustrated what these recursive programs behave like. I'm going to go ahead and stop that now and move on to the next recursive problem here. So this is greatest common divisor. I believe we gave you the iterative method for this as well. So you can see, yeah, here's another example of how you should be able to find these parts in a recursive method. So if I think about this, right, I'm going to keep going until q is equal to 0. Once q is equal to 0, this loop is going to stop, and I know that my answer is p. So without even looking at what the instructions are telling me, just based purely off of the code that I see here, I've already figured out what my base case is based on this while loop. This fits really nicely with the recursive method that we're about to write. Once this loop stops, once q is equal to 0, my answer is p. That's my base case. All right, let's go write that. If q is equal to 0, return p. Else. So this is probably where my recursive work is going to go. I believe the instructions tell you exactly how to write this out, but let's take a look at this and see if we can kind of figure out what's going on, right? I'm making some temp variable equal to q. I'm computing p mod q, and then p becomes temp, which is equal to q. So the repetition here is going to, let's see, what's happening here? The greatest common divisor of p becomes q. So q modulus with p mod q. Or, I'm sorry, it's going to be the greatest common divisor of p and q is equal to the greatest common divisor of of q and p mod q. Let me write that out. I believe that's it. I figured this out by working my way through the repetition of this while loop. So thinking about how these variables switch hands, right? At the beginning of this, I have p and q. At the end of this, what have my variables become? At the end of this, p has become q through the introduction of this temp variable, and q has become p mod q. And then I'm going to run the same thing over again. So that's how I determined how to plug in these values here, q and p mod q. That's where my repetition is going to keep occurring. there's no computation being performed on the way back up here. Notice that the way that this works is a little bit different than the way that this recursive method worked. Because this recursive method was computing an additional term and then doing some addition. Whereas here, I'm drilling down to the base case. The base case says, here's the answer. And then the recursive calls are just passing that answer back up. They're just saying, here's the answer, here's the answer, here's the answer, until it just pops out the end. That's kind of how this method is behaving in contrast to the last one. But let's run this and see if it actually works. Recursive GCD test suite passed. Perfect. Perfect. That one worked. All right. This next one is definitely tricky, but introduces some good concepts. So let's dive on in. We're going to use recursion now to create the reverse of the array that's been given. So I'm giving you this array of integers. I want you to make the reverse. And we showed you an iterative way to do this as well. So you can see that we're creating a new array here. We're going to check the length. If the length is greater than 0, we're then going to go through, iterate through half of the array, you can see, because the way that we create the reverse is by swapping. Swapping, well, it's not even necessarily swapping, right? It's just grabbing the appropriate values out of the array as we travel along. You can think of it as swapping the values, right? Grabbing the value from position, 2 in the first position, and then putting it in the last position of my new array. Grabbing the value in the last position of my new array and putting it in the first position of the old array and putting it in the first position of my new array, right? So we're kind of swapping values in a sense, but notice there's two arrays here, right? The array that's given to us and then this new array that's been created. And I'm pulling values out of the old array and putting them in the new array such that this new array is going to look reverse of the old one. We use a little bit of repetition to do that. We iterate through half. We iterate through half of the array. And we now need to turn this into recursion. So if we think about how we're going to do this recursively, right? Think for a second that we need a base case. And last time I looked at the conditions of my loop to help me with that. I started at 0, keep going until I hit the half of the length of the array. I'm not computing terms this time. It's based purely on position. Where am I at within the array? So the base case, I think, could be either one of these, conceivably, depending on how you want to approach it, right? But for the sake of our code, let's assume that we want the base case to, we were going to start at 0 like this one does and keep working until we hit over half of the length of the array, in which case we'll stop. There's a problem with that approach, though, right? If I try to write this, which I saw people doing in class, trying to write this method. So you might do something like, I want to check to see if the index is greater than or equal to array.length over 2, right? So, well, I don't have an index. Okay, well, I'll make one. All right, index is equal to 0. That's where I want it to start, correct? So I want my index to start at 0. If the index is greater than the array length array length dot 2, then I'm done. So I'll just return the array. It should be done. Otherwise, all right, now I can do some swapping. So I saw people do something like this: array at index. In order to get the other value, this is just a swap, right? So I could actually just say array. Let me think about this for a second. Sorry. Is equal to the array. So now I need to figure out what to swap it with at the back. So this is going to be based on the length of the array, the size of the array, dot length minus the index. So if the index is 0, this would give us array.length. But so that's not quite good enough. We need to subtract 1 from this as well in order to make it work out. So if the index is 0, then I swap it with length minus 1, which is the last address of an array. We learned that in module 3, correct? And then finally I can perform the last part of the swap, Actually, we could have perhaps pulled that from here as well, right? Last index array.length minus 1, or last index minus index. Yeah. Anyway, we could have worked the math out that way as well, but potato potato equals. Okay, so this performs the swap, but we now need to tell it to keep going somehow. So how do we? This would be our recursive call, right? To reversed array. But I need the index to go up 1. So let's maybe try index plus plus, right? And I guess I can, maybe return this. Here's a good stab at a recursive version of this. I saw many people kind of try it out this way. Let's see what happens when I try to run this. Let's see what happens when I run these tests. We can see that, nope, not working. It says do not return array parameter, expected not same for that one. But then for here, what's going on? I can see this test failed. Stack Overflow error. Oh, dang. That's not good. Well, wait a second. The index is supposed to be going up. If we walk this through the debugger and try to figure out what's going on. Oh, whoops. That's the last one. I went to the wrong program. If we try to run this through the debugger and see what's going on, what did I do wrong this time? Sorry about that. I don't know why. Did I not set a breakpoint? I thought I set a breakpoint. I did. Oh, I ran the wrong thing. It was supposed to be the test suite. Goodness, that's why I'm staring at the wrong thing. All right, cool. So here we are at the breakpoint. You can see the index is 0. If I go ahead and step through this, right? This must be the first test, so that the array was like length 0. Let's continue and see if we can do this again with a larger array. Here's one with where the array's actually got some stuff in it. All right, so this time the index is 0. It's not, we haven't hit our base case because this is a long array. We've actually got stuff in it. So it tries to do the swap. Let's go through and see. There we go. 3 gets swapped with 1. It increases the index to 1. That's all good, right? Now here's our recursive call. If I step into that, I can take a peek and I see, my index is 0 because that's the first line of my recursive call. I say it right here. This is one of the first things that I look for when people tell me they're having trouble with their recursive methods. Anytime I see something, a variable created up here, doesn't mean it's always going to be wrong, but this can be problematic to create a variable at the very beginning of a recursive method. And to understand why, I mean, remember that we're using this to do repetition, right? So here I can see, yeah, I did create a variable inside of this loop, but it's for a much different purpose, I think, than, or, it's being computed based off of this loop variable, right? And since this loop is being replaced by methods for performing the repetition, we need some way of having this index travel from one method to the next. That's the problem here, right? That's the problem that we're having. I'm increasing the index by 1, but then the next time I call the method, it doesn't remember that. It's making a new version of this that is going to be, independent of whatever I did in the last call. The way that methods communicate with each other is through their parameters, through their arguments. So in order to make that happen, I need to add another parameter here. But we don't want to mess up the original method. We want to leave this alone. So what I'm going to do instead is create what's called a helper. And the instructions speak to helper methods as well. helper methods are used to help us organize our code. There are some things that might need to only be done once. I can put those in the non-helper method, which is going to be my original method up here. And I'll show you some examples of what that might look like in just a little bit. The helper method is going to be where the recursion comes in. And the nice thing about the helper method is that I can add as many parameters as I want. So if I need to keep track of where I am, if I need this index variable to be communicated, right, from one method call to the next, I can just add a parameter for that, which is what I'm going to do. This is the most common reason why helper methods are introduced, which is a way to provide additional information for recursive methods to communicate between recursive calls. So now all of that information about my base case and everything is going to be moved down here. I'm actually just going to pick up this block of code and take it out of the non-helper method and move it down here. And since my helper method is what's going to be doing the recursion now, this recursive method call should be based on my helper, meaning that I will update the index this way. Okay? I'll update the index this way. Every time through now, since I'm adding one to the index and passing it in as a parameter, the next recursive call is going to know what position it should be swapping. Okay. Oops. Let's go ahead and see. Oh, wait, well, before I can do that, I have to go back to my non-helper method here. I mentioned that this is going to do any of the non-repetitive stuff, anything that is not recursive. At the very least, it needs to call the helper method. So think about what this information, what needs to happen to kick all this off. I'm going to say to reversed helper. It needs an array, and then it also needs an index. Let's start at index 0. That's a pretty good choice, right? That's the first index of an array. So this kicks off the recursion, lets this method do all of its recursive stuff, and allows us to specify where we want to start. Where we want to start this index parameter. Let's run these methods now and see where we get to. I don't need to debug it, I just want to run it. Okay. So it still says do not return array parameter. If I take a look at some of these tests, we can see that that says the same thing. Do not return array parameter. Here's another one. Do not return array parameter. I see a lot of people getting confused about this. And that goes back to the fact that in the original, we have two arrays. The one that we've been given and this new one that's been created. We want you to mimic this exactly. In this particular case, there's only one array that's being passed over and over, you know, it's being passed around, right? So where's the new one? Well, let's make it. Remember when I said anything that needs to happen once can go in the non-helper, so this array only needs to be created once. This is an integer array, I apologize. It's going to be the same size as the one that we've been given. And I now wish for this result to also be passed along so that I can kind of copy values from the original into the old one, or into the new one. Well, let's add another parameter, right? I want to stick this in there, so let's do that. Okay, I no longer need this temp variable because I'm going to be putting all of these into my result as opposed to the original. Result here. Okay, so with those changes now made, I'm going to rerun these tests again. Hopefully, well, I got some of them good, it looks like. So let's see, that one is okay, that one's okay. It's okay, it's okay. But it looks like I'm having trouble with odd numbered lengths, right? So for odd numbered lengths, something weird is going on. Maybe this should be strictly greater than, not greater than equal to. Let's try that again. All right, that did much better. Passed the odd length test now. And finally, this last one is a little bit of a tricky one. It's passing in an empty array. I need to check for that. But I only really actually need to do that once. That's sort of a special case. So I could come up here and say, you know, if array.length is equal to 0, return new int 0. Right? It's just going to be an array. Is that what it says in the iterative? Well, I mean, it's implied, right? New int array.length. Actually, I overcomplicated this, didn't I? I overcomplicated this, didn't I? Let's make the result array first. If array.length is equal to 0, return result. Else, go do some recursion. I think that'll make our tests happy. Let's run it one more time and see. Beautiful, beautiful, beautiful. Awesome. One more time, since this is such an important concept, I want to review this concept with you again. This idea of a helper method allows us to separate off the repetitive stuff, which is going to do our recursion, from the non-repetitive stuff. The recursive stuff, the repetitive work, is going to go inside of the helper method. So you can see here, my helper method is recursive. It has a base case, right? It does some recursive work down here after it swaps the values. You could have pulled these lines, you know, directly from here, almost, right? You could have even done this as well if you'd wanted to. So the contents of our helper method and the contents of this loop look very similar. The ending case here also very similar. So yeah, you can see all of those things kind of translate over to the recursive call here. Anything that needs to happen once, checking for this special case, creating this new copy of an array, you can see those things happen here as well. They only happen the one time. I'll kick those out into my non-helper method. So that's where any of the non-repetitive work goes. And then I will turn it over to the recursive repetitive work when I need to, when I'm ready. All right, there's one more recursive program for us to take a look at in this studio before I switch over and talk about the assignment for a little bit. The last recursive method is to look at this circles upon circles image. And so we can see, you know, I want us to think about what the recursive substructure is going to be here, right? We could do this iteratively. It is possible, but this is an example of a situation where recursion really is just going to fit nicely. And in order to understand why, I want you to notice the difference between, you know, what this is doing versus some of the recursive stuff we've seen in the prior parts of this studio. If I think of each method as drawing one circle, right? After this method draws one circle, I then next need to draw 4 more circles. One up here, one over here, one over here, one over here. And then for each of those 4 circles, I need to draw 4 more circles, right? And then 4 more circles. So the recursion that exists here, since it is two-dimensional in nature, we're drawing things on the screen, the recursion that exists here is also a bit wider as well. I'm doing 4 different things. I actually expect to see 4 recursive calls. I see the recursive pattern showing up 4 times, so I expect to see 4 recursive calls occur in my recursive solution. This is an approach called divide and conquer, and it does appear on the homework assignment as well. I'll discuss that in just a little bit. As far as the base case goes, I think that you can see these circles get smaller and smaller and smaller. Eventually they get so small that you're not even really going to see them anymore. So the size of the circles that we're drawing can be used as our base case. Once we get small enough, we're just going to stop. So let's go ahead and take a look at the code here, what we've been given. We're given the center point for the circle. We're given the radius of the circle. And then this is the radius minimum drawing threshold. This is what we're supposed to use for our base case. So if the radius is less than the radius minimum drawing threshold, I'm just going to copy paste that, we're done. You actually don't even need to write it this way. You could also do it the other way. If the radius is greater than or equal to, then we don't need to return. We'll do our recursive work, right? Draw 4 Actually, we haven't drawn the original circle yet, so let's do that first. Standard draw dot circle x center. It's just radius. Okay. So if I run the debug app now for the circle demo, I get a circle. There we go. I get one circle. But I'm not getting my other ones, so no recursive calls yet. All right, but I expect to see 4 more circles here, which means 4 more recursive calls, but I have to think about how those recursive calls are going to change. The center position of those 4 circles can be computed, right, based on where we are now. So I have this point in the middle. The center point of this circle is going to have the same y position, right, but different x. And the difference is going to be based on the radius. And I do that in both directions, both on the x-axis and the y-axis here. There's my 4 recursive method calls, right? They vary by the x and y-axis, as well as shrinking the radius. That's the part that actually guarantees that we eventually hit our base case. So I'll say circles upon circles. The center point will do x center plus radius for this one. The radius is going to, does it tell us how much to shrink the radius by? To create this image, we divided the radius by 3 at every level. So we'll do radius divided by 3. And then the radius minimum threshold. All right. I'm going to copy that line, actually, since I've already explained that I expect to see this happen 4 times. So there's my 4. I'll switch this to be minus the radius, and then I need to do the same thing but for the y-axis. So I'll take these off and do plus radius. Okay. So what this is saying is draw 1 circle in the middle here, and then go off and draw 4 more circles using the dimensions that we described. Let's run our debug app, our demo app, and see how we're doing. Whoops. You can see that I've got more circles than it expected, so maybe it's strictly greater than. Let's try that again. Oh, so it's not, I see what the problem is. I should only draw this, I need to move this inside the if statement. Yep, only draw it, yeah, there we go. That was my problem. Took me too long to figure that out, didn't it? Everyone makes mistakes. There we go, perfect. That looks good. That looks good. Yeah, we can see the recursive steps. This is fun. I like this. Cool. Oh, expected image not available. Ah. It gets too small. You can't actually see the difference after a while. But anyway, our solution appears to work. And so you can see the divide and conquer in action when you realize the fact that at the top level, right, this kicks off 4 more, but then each one of those kicks off 4 more, and each one of those kicks off 4 more, and each one of those kicks off 4 more, right? So by the time we actually do hit the base case, when the radius is, you know, less than or equal to, there could be potentially a lot of methods on the stack, because divide and conquer is going to spawn a lot of recursive method calls. You can think that it's going to grow very, very quickly. Okay, I believe that covers it for the studio, so I'm going to take a few more moments here and switch over to the homework assignment for this week, which is more recursive puzzles for you to do. I'd like to take a moment and just talk about each one of these. I think they're roughly ordered in terms of difficulty. I think the easier ones are up front, and the more difficult ones are towards the end of the assignment. So starting with exponents, right, we can see that we wish for you to create, I actually have this already loaded up for us as well. So let's take a look here. Starting with exponent, you're given the base and the exponent. And notice they can both be positive or negative. But you should consider the fact that if the exponent is negative, that's the same as computing 1 over the positive value of the exponent. So it's not actually a whole lot of extra work. If you can compute for positive exponents, you should very easily be able to make that check and compute for negative exponents as well. The repetition here, right? So where does the repetition come from? It's repeated multiplication. This is going to look very similar to the geometric sum that we did here, right? Not exactly the same. There are some differences to what we're asking you to do versus what we asked you to do for the studio. For one, we've got more parameters that you've got to deal with, and we're asking you to deal with negative values. That's an extra little wrinkle. You don't need a helper method for this. I've seen it done both ways, with and without a helper method. My inclination actually was to write it with a helper method when I approached this problem. I had my helper method, the recursive work, compute the positive exponent, and the non-helper method, do the other stuff. But it can be done both ways. So I'm happy to accept either approach, either way that you can work on it. For taking the sum of the array, right, some of the elements in the array, this one I think you probably are going to need a helper method for. I find it very difficult to conceive of a way that you'd be able to accomplish this array sum method without a helper method. So, I mean, I feel like people have tried it before, but based on, let me put it this way, maybe if you've been programming for a while and you know some expert tricks, you could work around it, but based off of purely what we know up until this point in the course, I would not expect you to be able to accomplish this without a helper method. So I think we're going to be looking for that pretty closely when you do the demo. And consider that it's going to be used for a similar purpose as for what we use the helper method for when we reverse the array. In fact, I actually think that taking the sum of the array is simpler than the array reversal problem in some ways. So definitely take a look at the studio code for the reversed array method, and especially how we use the index to track our location. Unlike this problem, you should not need this parameter here. You should not need to create any arrays. We're simply computing the sum. We're not creating an array or anything like that. So your helper method will definitely need something to track your location. Might need some other parameters as well. I want you to think about that, but could follow a similar approach to that reversal method. The next recursive method that we ask you to do is called dragon. It makes these things called dragon curves that look really cool. I think we've got some pictures for you here. So that one's not very cool, but as you get deeper and deeper, they do start to look pretty cool after a while. And the way that these are done recursively is by performing substitutions. So I grab the dragon curve, and then I perform some substitutions. Anytime I see f, I want to replace it with f minus h. Anytime I see an h, I want to replace it with f plus h. The problem that people run into commonly on this, I'll give you a big hint, right? Clearly there are two substitutions that we need to make here. I can perform a substitution on one character at a time. And yes, to another commonly asked question, you are allowed to use this substitute all method. We want you to use this method, even though it contains a loop. Yes, you are allowed to use this. We are giving it to you specifically for this purpose. Your solution should not use any loops, though. But the reason why substitutions are tricky is because this introduces more h's, right? But I don't want to substitute the new h's. I only want to substitute the old h's. So that's a pretty big hint. Think about it. Think about if there's a way that you can use the substitute all method to, substitute in something for new h that lets you distinguish that new h from an old h, so that when you perform the substitution for old h's, it doesn't affect the new ones. And then you may have to perhaps come back and perform an additional substitution to convert all of those quote-unquote new h's to the old h's once all of the substitutions are finished, so that everything will continue to work the next time around. But the recursive substructure here is pretty straightforward. It's actually very similar to the recursive substructure for geometric sum. In a sense, we are constructing a sum of terms, but instead of a sum, we're just performing substitutions instead. So in terms of the recursive structure, it's going to look somewhat similar to geometric sum. I think one thing that surprises people about this method once they're done, it's not a lot of code. This method can be done in a very small number of lines, handful of lines, 4 or 5 maybe, I think. Maybe a couple more than that. I don't remember off the top of my head exactly how many, but it's not a huge method. Does not need to be a lot of code. And then finally, there's max path length. This is certainly, I think, a difficult problem to accomplish recursively. But this uses that same concept that I was just talking to you about with the circles upon circles method, the divide and conquer approach. So that is what you're going to need to use here. And that should immediately, I think, tell you that, oh, I expect to see perhaps multiple calls, multiple recursive calls to make this happen. But let's take a look, and I'm going to assume that before you look at what I'm going to say, you've at least read the instructions and kind of understand the basic structure of this problem, or talk to somebody else to make sure that you understand the basic structure of this problem. I want to talk specifically about how we can apply recursion to this problem right now. So consider that if I'm at a particular spot, right, I could choose any particular spot on this grid. There's a couple of things that could happen. So if I'm at a spot that's false, right, that is false, I know the length of this path. There is no path here, right? There is no path on this spot. So the length of this path then is 0. There's no path here. So there is no length to be had. If I'm on a spot that's true, then I'm on a path, right? I know for a fact that there is at least one link in this path, the one that I'm currently on. So if I'm looking at this from a recursive perspective, right, I'm now imagining the recursive calls occurring on each and every single one of these spaces. So the first part of the recursive call is look down. If it's false, the length is 0. If it's true, I know the length is at least 1. But then in order to figure out what the maximum path length is from here, I have to look at all the possible options. I have to look in all 4 directions, right, to see what the longest path is in those 4 directions. There's where your recursive calls are going to come in. So look around in all 4 directions. Wait a second. We did all 4 directions in circles upon circles, right? It's a little bit different here, but also kind of the same. The last thing that I want to do is kind of work you through some pseudocode for this. I've already dropped some big hints, but let me drop you some even bigger ones now. Give you some pseudocode. I'm going to write out some, walk through this in English, step by step, and show you kind of logically how to work through this problem recursively, and then turn it over to you and let you turn that into code, which is still actually a pretty non-trivial task as it turns out. So let's start off with our base case. We already talked about the base case, right? If the spot that I'm currently on, represented by my current row and column, right? Here's my path, is false, length is 0, right? There's no path. Okay. Otherwise, I know the path is at least 1. But then I have to figure out what the longest path is in each of the 4 directions. So, north, south, east, west. These are your recursive calls. Right here. These are going to be your recursive calls. Once you get this information back from your recursive calls, look at the results and return the largest one. Okay? That's it. Here it is. This is the pseudocode for this problem. You know, there's a little bit more to it than that. One edge case that you will need to consider, right? I'm asking you to look north, south, east, and west. Well, what if I am on the border and I look south, right? That could be a problem. I could go off the edge of my array. How do you handle that problem? I didn't really talk about that. I'm going to let you figure out what to do about that because that is a problem that needs to be addressed. But as far as the general recursion goes, right, this should get the job done. Now, there's still a lot of work to do here. And I still really want you to understand, make sure that you understand, you know, how this works recursively, what this feels like recursively. But this should at least give you a good start in the right direction. Okay, I think that's it for me. I'm gonna let you all get to it. I know that this is a busy weekend. We got Halloween coming up. We got this recursion assignment coming up. But keep in mind that you do have late coupons as well. If you need to take some extra time to work on an assignment, that's totally fine. Please use those late coupons. That is what they are for. I'd also like to remind you that if you go to Canvas, there's a link to make an appointment with me. So if you want me to sit down and work through max path length in my office with you, I would love to do that. I do it with many students all the time, and I would love to do it with you as well if that would be helpful for you. So please go on to Canvas, take a look at the office hours, and use that link to make an appointment with me. I can talk to you about anything that you would like related to this class. All right, that's it for me. Have a good weekend, everybody. I'll see you in class next week.